Hi there guys, welcome to this video. My name is John, I'm a mathematics tutor and I specialise in providing tuition, support and guidance for A-level maths, A-level further maths and in particular 6-term examination papers and mathematics admissions tests. Welcome to this video where we're going to take a look at laws of indices. So laws of indices are something that you come across very early on in your A-level maths studies and probably you've come across them at GCSE as well. And there's something that you've really got to have a good grasp of throughout your full A-level maths studies, okay? Now, what you might not realise during your A-level studies is that there are all sorts of things that you're taking for granted when you're using laws of indices and when you're thinking about certain powers of real numbers, for example. Now, this is normal, by the way. I was exactly the same when I did A-level maths. So for example, if I saw something like this, the square root of 5 to the power of pi, I wouldn't necessarily have thought there was anything wrong with that expression. Okay, I would have just kind of taken it for granted that there is a number that is the square root of 5 to the power of pi. Okay, I can stick it in my calculator. My calculator gives me a number. It's okay, this is probably going to be irrational, so it's a decimal approximation that I'm getting from my calculator, but kind of gave me the reassurance, I suppose, that there is actually a number that corresponds to this. But how do we know? And second of all, how do we even think about this, or start, if we can, how can we try to start calculating the value of this? Okay, these are actually really not terribly easy questions to answer. But moreover, if we kind of take this as well, so the square root of 5 to the power of the square root of 2, if I can make sense of both of these, how do I know that this is going to be equal to the square root of 5 to the power of pi plus the square root of 2? That's what my laws of indices says. But how do I know that the number that corresponds to this expression times the number that corresponds to this expression is in fact equal to the number that corresponds to this expression? Okay, that's what we're going to be looking at in this video. So just to be clear, this video is not meant to be the kind of video where I just give you a few simple examples of laws of indices to help you on your way with A-level maths. There's already plenty of videos that cover all that kind of stuff. This is not going to be one of them. So if you are looking for that kind of video, this is not going to be the right video for you to be watching. What I'm looking to do in this video is to raise awareness, so draw your attention to certain issues and certain difficulties that there are involved with defining particularly irrational powers of real numbers, and also certain difficulties that come up with defining the various laws of indices. Okay, so this video really is for those people who have a higher level of interest in mathematics. And by the way, I understand that not everybody is not necessarily as enthusiastic as I am about mathematics, and I don't judge those people for that. That's just how it is, just in the same way that I'm not terribly enthusiastic about, I don't know, playing football or something. So I'm not making any judgment on those people, but this video is really for people who really want to develop their knowledge and understanding of mathematics to a deeper level, go beyond the specification. You don't need, what I'm about to say in this video, you do not need to know for your A-level maths, okay? I don't want to give the impression that you need to know this stuff that I'm going to be talking about for your A-level maths. You can get by in blissful ignorance of what I'm about to say and do perfectly well on your A-level maths. So it's really for people that are kind of looking a bit ahead, maybe want to get a bit of an idea about the kinds of things that you might be looking at when you get to, say, you're going on to do university maths. What kind of things will you be looking at? So the kinds of things that we'll be looking at in this video are definitely the kinds of things that you will be looking at in university maths. That's not to say that I'm going to go through everything in complete detail. All I want to do is just, again, raise a bit of awareness about these various issues and give some indication about how those issues might be resolved. Okay, so it's not going to be a comprehensive video. It's not going to be self-contained. But what I'd like to do as well is maybe give you some ideas about things that you might want to have a look at in more detail yourself. Okay, so there will be some gaps that I leave in the video from time to time. And these really are an invitation for you to maybe go off and do a bit of your own research if you're interested enough. Okay, you don't have to, but hopefully it will give you a bit of motivation to just go the extra mile. Okay, if there is anything, by the way, that I say that is not terribly clear in this video, please leave a comment in the comments section, and feel free to ask for some clarity. That's what I'm here for, to help you. That's what I want to do, to help you. So there will be some things. This is entirely unscripted, by the way, this video. I've got a few notes here on my computer, just to give me a bit of a prompt every now and again if I need it. But generally speaking, this is an unscripted video. So some things I might not explain terribly clearly. If that's the case, let me know. I can always remake the video, do a better job of it further down the line or whatever. But if there's anything that you need any clarification on, just get in touch. Okay, just get in touch. I can direct you towards some other resources that you might be interested in if that's what you want to do, and so on. Okay, so what we're going to be doing is we're going to be looking at how to define powers of real numbers. Okay, sounds boring, right? It's not, if you're into that kind of thing. This might seem like an obvious thing, right? So square root of 5 to the power of pi, well, what's the big deal? There's all sorts of difficulties here, okay? That from a mathematical perspective, we have to resolve these. We have to resolve these issues. We have to get to the bottom of them, and we have to deal with them. As tedious as it might be sometimes, and believe me, there are some things that you will have to do when you go into high-level maths that are terribly tedious, that seem very, very obvious. But they seem obvious really because maybe you've just always taken them for granted. Okay? So in the same way that when people are first maybe introduced to differentiation, maybe they're just given the rule. When you differentiate x to the power of n, you get nx to the power of n minus 1, and they're quite happy using it. Okay? They can differentiate powers of x. And then all of a sudden somebody comes along and says, oh, actually that rule comes about in this particular way. You can use differentiation from first principles to prove it for positive integer powers and things like this. A lot of people will kind of say, well, why would you want to do that? Why can't you just use the rule to differentiate? And because they either don't care in some cases, or they just don't necessarily grasp that rule has come about in a particular way. And it's often been quite a laborious process by which that rule has actually come about. And it's the product of a lot of thought, a lot of deep thought and intricate thought. Okay, you're just being potentially given the end product. And that's kind of what happens with your laws of indices at A level. You're given the end product. And you're not really given much indication about where these have come from. Maybe it's kind of touched on very briefly, but you don't go into a lot of detail. And this is fine, by the way. You don't need to know this stuff for A-level maths. But as a mathematician, you do have to face these issues at some point. So hopefully this video will give you a bit of insight into how that might work. Okay, so let's have a look. Where do we start then? Well, arguably, we need to make sure that we're clear about what we mean by real number, because we're going to be talking about powers of real numbers. This, again, is something that you might kind of take for granted. In fact, you almost certainly will take for granted at A level, that there is a set of numbers called the real numbers. Okay, and I certainly didn't give too much thought as to how that might be defined, that set of numbers might be defined. So you're often told, if you do venture to ask at A level, ask your teacher or something, what is a real number? You might be presented with some kind of wavy-handy, wishy-washy definition, like, or a real number is any number that you can think of, or a real number is any number that your calculator can give you, or something like that. These definitions are completely unsuitable. They don't do the job. They don't define real numbers at all. There's much more precise definitions of real numbers, but I'm not going to get into them in this video. We are going to accept and take for granted that there is a set of numbers called the real numbers, because it's a whole different subject. If you are interested in that, by the way, let me know, because I can make a video on that in future. I'm not saying I will make a video, but I can do if there's enough demand for a video like that. So if you are interested in a video where I talk about how the real numbers might be defined in a more precise sense in mathematics, just let me know. Okay, so we're going to start with just a real number, x. And for the time being, we're not going to place any real restriction on x. It could be positive, it could be negative, it could be 0, it could be rational, it could be irrational. And we're going to consider the expression x to the power of 1. Okay. By the way, for the time being, for the rest of this video, pretend that you've never seen powers of numbers before. Pretend that you've never come across laws of indices. Pretend that you don't know what I mean by x squared or x cubed and things like this, because we're going to be building up from the bottom. Okay, we're going to be taking the most basic definition and we're going to be building up from that. Very common thing to do in mathematics, and it's something that you'll have to do repeatedly if and when you get to university. If you're doing mathematics, you'll have to do this time and time again, where there's something that you know, or you think that you know quite well, and you've kind of taken it for granted, but actually there's certain difficulties involved with that concept that now you've got to almost pretend that you don't know about it, and you've got to start from its logical beginning and kind of build back up to where you were before. That's what we're going to have to do here. So it's a logical development of indices. Okay, how we have to understand indices, and we're taking the basis is this expression here. The basis of everything is this expression here. What do we mean by x to the power of 1? Well, understands that I have potentially a lot of theoretical freedom about how I choose the value of this. I could, if I really wanted to, say that x to the power of 1 is 5 times x. And you might say, but it's not, right? X to the power of 1 is equal to x. It's obvious. Yeah, it's obvious because maybe you've taken it for granted that that's how it is. But understands that I could define this to be whatever I wanted it to be, in theory. But it's just that I want things to work in a particular way. We want mathematics to work in a particular way. We want it to make sense. We want it to have a certain consistency about it. So even that theoretical freedom that we have is kind of massively restricted. And it's restricted so much that the only really sensible choice here of definition is to set x to the power of 1 equal to x. Okay. So this is a definition, and it comes about really because I want mathematics to work in a particular way. Okay. So once I've got this, then I can start to build on this, and I can start thinking about, well, what do I mean by this symbol, x squared? Well, by this symbol, I mean x times x to the power of 1, which of course is x times x. No surprises here, right? But again, in theory, I could define this in any way that I wanted to. I could define this to be equal to 16.972. Why? Because I can. It's just I don't want to, because it doesn't make sense. It doesn't make things work in the way that mathematicians want things to work. Okay? So once we've got that, then we can move on to x cubed. And we get x times x squared as our definition for this, which of course is equal to x times x. Okay, so what we're going for here is kind of an inductive definition of x to the power of n. Okay, So an inductive definition, think about sequences defined inductively, where you're given the first term of the sequence, and then the second term is defined in terms of the first term of the sequence, the third term is defined in terms of the second term, and therefore ultimately in terms of the first term as well. The fourth term is defined in terms of the third term. It's kind of that idea. Obviously, you can get much more complicated recurrence relations or inductive definitions, but that's the kind of idea that we're going for here. So we've got x to the power of n. We're going to define, because it makes sense for us to do so, we're going to define this to be x to the power of x times x to the power of n minus 1, which is equal to x times x times x times times x times x, and then I don't know how many brackets I'm going to need over there. But here I've got n x's, okay, n x's. Now this is really cumbersome, right, with all the brackets and everything. One of the properties of real numbers is the associativity property, which means that I can group together, when I'm multiplying real numbers together, I can group them however I want. Okay, so if I've got 2 times 3 times 4, I can do 2 times 3 first and then multiply by 4. Or I can do 3 times 4 first and then multiply by 2, for example. And this, you can extend this idea to much more complicated expressions, much longer products of real numbers. So because it doesn't matter how I group them together, the brackets are really serving no purpose for me here. So what I can do is I can write this as x times times x, where there's n x's. Okay, so I just suppress the brackets and I just end up with this. And similarly here, for example, I could write x times x times x. Okay, so that gives us, that tells us what we mean now by positive integer power of a real number. Okay, positive integer power of a real number. This doesn't tell me what it means for x to the power of square root of 2 or x to the power of minus 2/3 or anything like that at this stage. We have none of that. This is where we are. We've just got positive integer powers of x. Well, once I've got these definitions, then I can think about this expression, x to the power of n times x to the power of m. So this is going to be equal to x times xn times x times x times x m times. But that's no different to me just multiplying x by x by x by x n plus m times, which is equal to, of course, x to the power of n plus m. So this establishes one of the rules of indices, one of the laws of indices. And it's this law, this is one of the laws of indices that we really want to preserve once we start extending the range of applicability of n and m, which values n and m can take. So even when we extend n and m to negative powers, to rational powers, to irrational powers, we want this rule to be preserved. So even though, again, we have this theoretical freedom about how we define these terms, it all comes back to we want things to work in a particular way. And one thing that we want to make sure is maintained throughout is this rule. Okay. There's also another rule, which is this one. X to the power of n to the power of m. Oh, that went a bit wrong, didn't it? X to the power of n to the power of m. Because, well, I know what this means. X to the power of n is just a real number, by the way. So this is going to be x to the power of n times x to the power of n m times, x to the power of n. There's m of those. And then each of these x to the power of n's can be written as x times x n times x times x n times x times x n times. So there's n, and then here we've got m groups of n. Well, that's another way of saying m times n. okay, or n times m, whichever you prefer. So this is equal to x to the power of n times m, which again is another law of indices that I'm sure you're familiar with, but it comes really down to this definition, right? If we didn't define things in this way, things would not work in this way. And because we want things to work in this way, this is kind of what we were driving at, it forces us, in a sense, to define things in this way. It forces us to ignore our theoretical freedom about how we define these things, and it kind of boxes us in a certain way. There might be other ways, by the way. I'm not saying that this is the only way, but it's really the only sensible way. Okay, there might be other much more complicated ways that still manage to make these laws of indices work. Stuff like that does happen, okay? But this seems to be the sensible way for things to work. So this is good. This is good. We understand now what we mean by positive integer powers of real numbers, and we've got a couple of properties now that we've derived, and it's those properties that we really want to make sure we preserve. So what's the next step? Well, let's add another number in here, or another symbol, x to the power of 0. For the time being, I'm just going to ignore. There is one particular value of x that I'm not going to talk about it right now, but I will address it further down the line. Some of you will know which value I'm talking about. But how do we make sense of this? Well, again, I want things to work in a particular way. So in particular, I want, for example, x to the power of 0 times x to the power of m to be equal to x to the power of 0 plus m, which of course would be equal to x to the power of m. This is what I want. This is what I'm going to use to motivate my definition, part of what I'm going to use to motivate my definition of this. Similarly, I want x to the power of n times x to the power of 0 to be equal to x to the power of n plus 0, which equals x to the power of n. And I'd also like x to the power of 0 times x to the power of 0 to be equal to x to the power of 0 plus 0, which equals x to the power of 0. These are the desirable properties that I want to follow from this. Well, how can I get this? Well, one way, I'm sure you've guessed, is that I set this equal to 1. Rather than defining it as something like, I don't know, e to the power of 69.73, which I could do if I really wanted to, and I wanted to be a bit obnoxious about things. But then none of these rules would work. So based on what I see here and my desire for these rules to work in this way, it makes sense for me to define x to the power of 0 as being equal to 1. Okay, so why is x to the power of 0 equal to 1? Because we choose it to be. Because it makes sense for it to be equal to 0. Okay, so now I can check this. Okay, x to the power of 0 times x to the power of m is equal to 1 times x to the power of m, which is x to the power of m, which is x to the power of 0 plus m. That works, fine. X to the power of n times x to the power of 0 is x to the power of n times 1, which is x to the power of n, which is equal to x to the power of n plus 0. Perfect. And similarly, I'm not going to go through it, but x to the power of 0 is equal to which is x to the power of 0 plus 0. Also, I can check that x to the power of n to the power of m works for various combinations. So x to the power of 0 to the power of m, and x to the power of x to the power of n to the power of 0. I'm not going to go through these. I'm going to leave this for you to have a go at yourself. But I can check that this rule also is preserved under this definition, which is a bonus for me. Okay, that's exactly how I want things to be. So now, these rules that we have, this x to the power of n times x to the power of m equals x to the power of n plus m, and this rule, I've extended them from just positive integer powers to non-negative integer powers. Might seem like a small step, you know, I've added one extra possibility to my powers, but we're making progress, and sometimes progress is a bit slow, sometimes it races on ahead. But it's essential for us to deal with this situation. Now, there was one case that I didn't explicitly deal with, or that I've kind of ignored, and that's this one, okay? This expression, 0 to the power of 0. What do we mean by 0 to the power of 0? This is kind of an exceptional case. Again, you could use your theoretical prerogative to define this however you wanted, okay? Some people will just say, well, may as well set this equal to 1, then it matches, it kind of fits the pattern, right? It just matches this pattern. And that's fine. There's nothing wrong with that. Some people will say, no, I'm going to leave this undefined. I don't like this expression for whatever reason. I'm going to leave it undefined. That's fine. You could define this as 2 if you wanted to. You could define it as 53. I'd say it doesn't make any difference, but I guess it kind of does to a certain extent. I'm not really bothered. I usually just consider this to be equal to 1. But really, it's something that it doesn't come up that often anyway, that I don't really make much of a fuss about it. But you could define this however you wanted. Some people leave it undefined, some people define it as 1. And they're the kind of two sensible options to go for. But anybody that says that this is equal to 1 and it can't be equal, and gives the impression that it can't be equal to anything else, is completely wrong. Okay? Anybody that proves that this is equal to 1, well, I don't really understand what exactly they're proving, because you can define it however you want. Okay? There's nothing really to prove there. So make what you want of that expression. Okay? I'm not necessarily going to include it or exclude it. It doesn't really affect the rest of the way that we're going with the rest of the video. Okay, so where next? I think the next logical step for us to go would be negative integers, right? So let's have a look at something like how can I define x to the power of minus n? So I'm going to assume here that n is a positive integer, possibly 0. So x to the power of minus n is definitely going to be negative, okay? How do I define this? Now, of course, at this stage, you might be saying, well, it's obviously 1 over x to the power of n. Obviously? Maybe, but maybe there's also other possibilities. We really need to make sure, okay? Again, this theoretical freedom comes into play. I could say that this is just equal to whatever I want it to be. But let's have a look. What do we want from this expression? How do we want it to work? Well, one of the things, I guess, is that we want this to happen. X to the power of n times x to the power of minus n to be equal to x to the power of n minus n, or plus minus n, should I say. X to the power of n plus minus n, because that's the rule that we want. Remember this rule, x to the power of n times x to the power of n equals x to the power of n plus m. We want this rule to work. So if this rule is to work, this is what it must look like. Okay? Well, that's going to be x to the power of 0, which is just going to be 1. Okay? So in other words, I want x to the power of n times x to the power of minus n to be equal to 1 if this rule is going to work. So what does that mean then? Well, it means that x to the power of n times something is equal to 1, which means that this something must be the multiplicative inverse of x to the power of n. Okay? Well, what's the multiplicative inverse of x to the power of n? It's the reciprocal of x to the power of n. So this must be equal to 1 over x to the power of n. Okay, so it makes sense for me to define this as this, 1 over x to the power of n. Of course, you already knew that, right? But now we're kind of giving a justification as to where this comes from. Why do we think of x to the power of minus n as this? Because if you think about how you were originally introduced to powers, so x squared, x cubed, or 5 squared and things like that. 5 squared means 5 times 5. 7 to the power of 6 means 7 multiplied by itself 6 times. But of course, once you get onto negative powers, this kind of breaks down, okay? If you've got 5 to the power of minus 2, how do you multiply 5 by itself minus 2 times? Okay, so we're just giving an interpretation of it, okay? We understand it as meaning this. And once we've got this definition, we can systematically go through these rules. So x to the power of n, x to the power of m equals x to the power of n plus m, and x to the power of n to the power of m equals x to the power of nm. And we can verify that these rules work when under this definition as well. So if we allow n and m to be just integers, positive, 0, or negative integers, we can verify these rules work with this definition. And that's kind of a tedious thing. I'm not really going to go through that too much at this stage, but that is something that you can do. You just got to consider various possibilities. It takes a little bit of time, different cases that you've got to consider. So I'm not going to go through the nitty gritty of that, but just to give you a bit of an idea, you do need to check these rules work under this definition, because then things are working as we want them to, okay? And it justifies our choice of definition of this. So where to next? We've got the integers completely sorted. We understand what we mean now by powers of integer powers of a real number. And by the way, there's no restriction here on the real number x, except for when we've got negative powers, we can't let x be equal to 0. And if n is equal to 0, then maybe we can exclude x equals 0 as well. So there are some minor restrictions in that respect, but generally speaking, we don't need to worry too much about that. Okay, so where to next then? Well, the next stop is rational powers. Now we're going to have to do this in 2 stages. Okay, first of all, we're going to consider powers like this: x to the power of half, x to the power of a third, x to the power of a quarter, and more generally x to the power of 1 over n. We're going to figure out what we mean by those first, and then we're going to go for more general rational powers. Okay, so again, our theoretical freedom comes into play. We can choose these however we want, okay? But our choice really is going to determine whether these rules that we want to work in a particular way, whether they do work or whether they don't, okay? So let's have a look. If we want things to work, how are things going to have to work? Well, let's say we've got x to the power of, let's take the rule x to the power of n to the power of m equals x to the power of nm. Let's say I want this rule to work with my particular choice of, say, x to the power of a half. Then what I'd need to see is something like this happening. X to the power of a half squared must be equal to x to the power of a half times 2, which is equal to x to the power of 1, which is equal to x. Okay. Well, what number must this be then? Again, this is assuming that this rule works. Okay, I'm choosing x to the power of half in such a way that this rule works. Well, this must be the square root of x. So here, okay, yes, we're assuming that x is going to be a positive real number here. Okay, we don't want to be dealing with complex numbers. We want to stay entirely within the realm of real numbers. We don't want to be spilling out into complex numbers here. So we definitely need x to be really restricted to positive real numbers. Why so? Because what do we mean by, well, if we've got a number, a squared equals b, then that means that a is equal to, by definition, the square root of b. A is equal to the square root of b. The square root of b is that number which, when multiplied by itself, is equal to b. Okay, well, that's what we've got here. We've got a number which, when multiplied by itself, or when squared, and we understand what this means, is equal to x. Well, that must be then the square root of x. It can't be anything else. Excuse me. If we want this rule to work. So this must be equal to the square root of x. Similarly, the cube root of a number. So the cube root of x times the cube root is that number which, when multiplied by itself 3 times, or which, when cubed, is equal to x. So from this, it would make sense for me to define x to the power of a third as the cube root of x. Not difficult to see that it would make sense for me to define x to the power of a quarter as the fourth root of x. And similarly, x to the power of 1 over n as the nth root of x. Okay? Because then I kind of get this behavior in each case. So I'd get x to the power of 1 over n to the power of n is equal to x. Well, a number raised to the power of n, which equals x, must be the nth root of x. And a certain property of real numbers guarantees that these roots are going to exist. Again, that's kind of something else. I'm not going to get into that. How can we guarantee that, you know, the nth root of a certain positive real number is going to exist? That's a separate issue. We're going to take that for granted, but it does. Okay. Right. So once we've got this, and we've kind of got the impression that this is going to preserve this rule, and we can check as well if we really want to that it preserves. Our definition preserves this rule, which I'm not going to just yet because I'm going to do it in a general case. Then, okay, we can start thinking about what do we mean by much more general rational powers of x. Okay. So if we think about the expression x to the power of p over q, for example, what do we mean by x to the power of p over q? Well, again, coming back to this rule, if I want this rule to work, it suggests that this is going to be equal to x to the power of 1 over q to the power of p. In other words, x to the power of p over q is going to be the qth root of x to the power of p. And yes, I'm assuming here that p is an integer and q is a non-zero integer. Okay, so then I know what all these expressions mean. I know what x to the power of 1 over q means because it's one of these. Q is a non-zero integer. And I know what it means to raise that number to the power of p, because p is it could be a positive or negative integer. It doesn't make any difference. But I understand what these mean, right? So I understand what x to the power of p over q means. That's how I can define it. If I define x to the power of p over q in this way, then it kind of makes this work, which is good. Although I would need to check it in a much more general setting, which I'm not going to do here, which would be x to the power of p over q to the power of r over s, where p over q and r over s are rational numbers. What you'd find is that this is equal to x to the power of pr over qs. I'm not going to go through this, the individual steps of it, but I am going to check this one. I'm going to check that this rule works for these rational powers, because this is a little bit fiddly, is this one. So let's have a look. So let's say n is equal to p over q and m is equal to r over s. Rational numbers, p and r are integers, q and s, they're non-zero integers, all that sort of stuff. Okay, so we've got x to the power of n to the power of m is equal to x to the power of p over q times x to the power of r over s. Now, this is equal to x, because p over q, the fraction p over q, or the rational number p over q, is equal to the rational number ps over qs. So therefore this is equal to x to the power of ps over qs. And in a similar way, this is equal to x to the power of rq over qs. Which this expression is going to be the ps and qs are both integers. Ps is an integer, qs is a non-zero integer. rq is an integer, qs is a non-zero integer. So I know what it means then to take the qs root of x and raise that to the power of ps. Okay, qs is an integer. Does this seem a little bit fiddly? Unfortunately, this is how it is. Okay, and this is therefore the qs root of x to the power of rq. But I know that this works for integer powers. I've already established that. Well, that's what I've got here. I've got a real number here. It doesn't matter what that is right now. But these are integer powers. So therefore, this rule works. So this is going to be the qs root of x to the power of ps plus rq. Which by definition, by our definition, is equal to x to the power of ps plus rq over qs. Which, if we do a little bit of simplification, we get x to the power of p over q plus r over s, which is equal to x to the power of n plus m. Magic, okay? So our rule works now for rational powers of n of x. So n and m can both be rational numbers, and we still get that our rule works. Fantastic. You can check it in for this as well. I'm not going to go through that. I'm going to leave that for you to do. Otherwise, the video is just going to go on forever. But now we're really cooking. Okay, we've got all of these exponents catered for now. We've got rational powers. We've got integers. We've got zero. We've got positive, negative integers. All of that covered. But we don't have irrational powers accounted for. How do we talk about x to the power of, say, square root of 2? Okay, that's our next stop. And that's where things are going to kind of wrap up for us. You might be pleased to hear. Okay, so what do we mean by an irrational number? Well, an irrational number is a number that is not rational. Okay. Something that I'm going to kind of present without proof here in this video is that every irrational number can be thought of as the limit of a sequence of rational numbers. Not a unique sequence, but there might be. So if we take square root of 2, for example, there's all sorts of sequences of rational numbers which converge to this number that we call square root of 2. Now this is quite an intricate thing. This is something that you will do at university. It takes a long time to kind of set things up in the right way. Again, if you do want a video on this, let me know, because I can make a video on this. It's just I don't want to go into detail with it here. If we take one of those sequences of rational numbers that converges to our irrational number, we can define our power, our irrational power of a real number in terms of this sequence in a way. So let's say A is an irrational number. And let's say we've got a sequence A1, A2, A3, of rational numbers. So these AI are rational. And they converge. So if we take the limit as I approaches infinity of AI, this is equal to A, right? This we can always choose such a sequence of rational numbers which converge to our irrational number. And it doesn't matter whether it's square root of 2, pi, e, whatever, okay? We can always do this. One of the properties of real numbers. Okay, so because I understand rational powers of real numbers, then I can also consider the sequence x to the power of a1, x to the power of a2, x to the power of a3, and so on. And I can think, what would I like this to converge to? Again, I can kind of, actually I don't have theoretical freedom here about how I can choose this so much. I don't think. Maybe I do, I don't know. But I would like this to really converge to, so if I take the limit as I approach as infinity of x to the power of ai, I would like this to converge to x to the power of a. Or that should be equals, actually. I would like this limit to be x to the power of a. And that's what I can do. I can define the limit of this sequence to be this number. In other words, I can take, if I've got x to the power of a, I can understand this as being the x to the power of the limit from I to infinity of ai, where ai, the ai's are a sequence that converge to a. I can understand it as that, and then I can say, well, this is equal to this limit here, okay? Because I know what these mean. X to the power of ai, I understand what each one of those means. Okay, so I'm defining effectively irrational powers of a real number in terms of kind of sequences of rational powers of the same real number, or limits of sequences of rational powers of my real number. And that's it. And I can verify that all of the rules, x to the power of n times x to the power of m is equal to x to the power of n plus m, and x to the power of n to the power of m is equal to x to the power of nm, and so on and so forth, that these holds true in this case. It does mean that I've got to use some other properties of sequences and limits of sequences, but it all falls into place, right? So then we have it. We've figured out what we mean by powers of real numbers, whether the powers be integers, rational numbers, or irrational numbers. We know now, and we know that these rules work for irrespective of the values of n and m. Okay, now it's different. Start bringing complex numbers and things like that into it, it gets much more difficult. But that's it. Okay, for real numbers, we're done. So there's a lot of details that I've kind of left out. I've left those for you to investigate for yourself. But if there is anything that you'd like me to clarify, just let me know. Okay. So I think I've said enough in this video. It's gone on a little bit longer than I expected. But please show your support for this channel by hitting the subscribe button and hitting the like button. If there is anything else that you would like me to make a video on, just let me know. I don't make these videos because I get paid for them. I make these videos for free and because I want to help people. I really want people to excel and reach their true potential, okay, with their A-level maths and getting into whichever university. But I can only do that with sufficient support, okay? So please show your support for this channel by hitting the subscribe button. If there's anybody that you think might be interested in these videos, share them, and hopefully they can show their support as well. So that brings us to the end of this video. So all I'm going to say is thank you very much for watching, and I look forward to seeing you in the next video. Cheers, guys.